Welcome back to High Performance Computing, Lecture 1, a general overview of high performance computing. Within the first part already we discussed several aspects, and in this end we can of course also acknowledge that having a big overview in high performance computing will probably fill much more than 2 times 40 minutes. But still, the key message to take away that I bring you different topics that we will handle in the course and also refer to different lectures. But here and there, we also, look around already in details. Really, when you think about system architectures, knowing about multi-core is important, that the network interconnect is important, and so forth. So, having now understood a little bit in the first part these things, and also several, let's say, terminologies really. So what makes a supercomputer, why the top 500 is important, and why maybe also HPC is basically a kind of element of 4 different aspects, not only, hardware, what many of the people think is HPC. So HPC is equally about theories, using basically physical laws with numerical methods, limits. Amdahl's law you will basically consider in terms of data. That will be an important part later in the course. And of course, then also the whole idea of the different technologies that matter. So we see a heterogeneity in technologies. I was mentioning LUMI with Instinct cards versus NVIDIA, perhaps in many other JU supercomputers. So there's lots of variety really. And then of course, on top of it, you have all the software libraries that have to follow suit with these, right? So it's a wild mix of different technologies, hence the ecosystem technologies that will be also now the second name here, will basically be built on these basics from part 1, while this here is part 2, going here and there a bit more in detail, but also into different areas which have in the last couple of years gone significant momentum. And this is again the deep learning then really fueled by GPUs. We will talk about this again, although we had already some insights in the prologue to also show you the course content. Here we will still build up a little bit of knowledge in order then to also dive later in other lectures. As I said, with lecture 5, 6, 7, we will then go to GPUs, deep learning, machine learning. But as this course is just starting, let's build one by one. So by HPC ecosystem technologies, we want to understand a little bit that the system software that you have on this HPC systems is not at all something that is directly comparable to a laptop. Of course, there are similarities, and one of it is, of course, an operating system. So that's what all of you mostly know. You have some Linux, Windows, or Mac, and it runs the whole system, but HPC system has some added elements, and one of it is, for instance, a scheduling system. We will talk about this basically in the next practical lecture 1.1. I will demonstrate the Slurm, basically cluster access, and the reason is here that you have concurrent access to supercomputers from many different users at the same time, right? So this has to be digested. Many different users at the same time use a computer, right? So this is something as if you would give your laptop away in class and 40 people want to use your laptop at the same time. So hence, this would be not so easy. And of course, the supercomputer or HPC machine or cluster in smaller terms might have the capacity, but you also need to have the software environment and the, let's say, the idea that you don't interact with each other, don't overwrite code, and have the capacity to really run at the same time, because that's something someone has to keep track on. So hence this will bring us to an idea of a system called scheduling, which has a large theoretical parts, so different scheduling algorithms. Some are better than others. Some have, of course, benefits of, backfilling, for instance, where you can have holes in the schedule filled if you want. And the whole approach is also a little bit alluding to the idea of doing batch processing. So that's also something which many students don't really have a grip on. So many people use Windows on laptops and so on. So batch queues refers here that you submit a job to this cluster and you are scheduled in a let's say, queue until there's space for you to run on this HPC system. In other words, it may be take an hour before your task, your application, whatever it is, the HPC system should do, actually is running. And this is something, which needs a proper system to manage all of that. So not only the different users, but also the idea of how I can arrange that all the nodes, the CPUs, GPUs have time for your application at a specific point in time, not affecting other users, of course, that actually do the same thing. They also submit to the queues and are waiting. Hence, this will be also something we look into deeper. And this is a whole range of different systems that are available there. We put a bit an emphasis here in the course on the Slurm scheduling system, and we will make some demos already in the next practical lecture. Then the whole approach of architectures that you have seen, combining very, very different, let's say, technologies in one huge rack, for instance, already bears lots of problems. So not only is the system load, how many people are using the system right now, but also perhaps are there errors? We call that system health checks. Is the system still alive, or how do we have overheated CPUs? Do we have a problem that the storage is not connected anymore? So also here we have different systems that we all would count into the HPC system software, like LLVIEW, Ganglia, and so on. Hence, also a larger idea of a system which you can maybe, of course, compare a little bit to your process list, right, that you would have on your computer, on your laptop. But here we talk much more across different nodes, memory usage across different users, et cetera, et cetera. So much more bigger scale again. And then there are some others where, for instance, performance analysis in previous iterations of the course, we had there much more emphasis on performance analysis systems. Scalaska, Vampire are all those that you would need if you program in parallel to then really get the best performance out, because it will do an analysis of the performance. Does it really use, let's say, the system efficiently, or do we have bottlenecks in the parallel programming, which we can fix actually by program a little bit different. So these are all large systems like Scalaska, which of course is then there for the experts in parallel programming. We put more and more emphasis in AI, giving its growing, let's say, momentum in HPC. But if you are in HPC, chances are you will also see these systems, performance analysis systems, to really try to get the best out of your code. And then the whole notion of SSH gives already to you one of the aspects which is often also seen as a problem in HPC, if we talk openly about this. And this is that the access to HPC systems, given Unix, given the whole variety of SSH keys and the whole system idea of Slurm job scripts that we will learn also in practical lecture 1.1, it's not obvious to you. We will see how that materializes when I show you how to schedule jobs. It's not that you just come and say, hi, I want to run this application. So you have to do specific job scripts, which can be tricky. Knowing already very much the underlying or low-level details of the HPC system. Hence, there's a whole range of so-called middleware, or more recently also maybe cloud access to HPC systems, which enables us to simplify the access. So you would pick an application and then run it without having the need to really basically craft large Slurm job scripts, right? So they're basically on top of scheduling systems if you want, like the Rescale system, but there's also the Unicore system, for instance. Many of them, Unicore will show you in a moment, because there's also the so-called Jupyter that you can also see a little bit in the class of middleware, making it easier to have the access to HPC systems. Hence, this slide should show you that a HPC system software environment is not at all easy. And this is particularly true also because of the batch that you will learn in practical lecture 1.1. So I think it's for many of you not directly obvious what that means with a batch. I know that from experience. That's why we do immediately after this lecture 1.1, where I show you the aspects of scheduling. And what we see is more and more also a momentum with AI and machine learning, deep learning, and several different, let's say, more Python-oriented codes to really go to interactive supercomputing approaches. So this has several benefits. So you see here the Jupyter, for instance, in Jülich that we will also use in the course, Jupyter Lab Access, which means we can go there by username, password, essentially, and log into such a system. And another element is that once you have, let's say, started such an instance of the Jupyter notebook, some of you know that already from my cloud course, of course, and we go back to this here also in the HPC course. But you see that you're basically directly scheduled on some of the nodes. Hence, it's sort of interactive, right? There's no batch waiting for that. And in the background, lots of things are happening to enable this. Hence, we talk about this middleware term I was alluding to. You see here one of the middlewares called Unicore, which is actively working together with a so-called Unity Identity Management project and program and tool, which is essentially one of the challenges as well. Because if you remember, we had a username, right, associated with some of the public keys, and then your matching private key gave access. Hence, there needs to be a whole range of identity management for different users if they want to access a system and then also submit jobs. Here you see one of the example jobs, which is also interesting to explore with enabling interactive supercomputing. If you want to maybe explore the breathing through the nose here in order to understand medical operations, essentially, then an interactive access to basically interact with the simulation during the runtime can be quite interesting. And the same is actually true if you do AI modeling on Jupyter. It's much more comfortable than submitting again a Slurm job script, again a Slurm job script, etc. Of course, if you are scaling very high, you use maybe 1,000 GPUs in parallel, then chances are that you already mastered this. And some of my PhD students, of course, use that way, combining then, for instance, TensorFlow with Horovod over many different GPU nodes, and then have the application submitted via batch. So still for exploring, for the initial baby steps, having a Jupyter access, which is really a simplified access, as you will see throughout the course when we do the practicals and my demonstrations, is of course also more and more requested and also more and more possible. However, I would say here and there it has still, of course, scalability limits. So when you talk about the interactive access particularly, but I will show you more on these aspects of scheduling and Slurm and so on Area on Deep in the next practical lecture coming up. For the HPC system architectures, there are lots of words and terminologies. And even if we have here in older systems, the supercomputer Blue Gene line, which is actually not anymore available from IBM, it was quite a long period where they had the Blue Gene L, Q, and P different systems, which we also had in Jülich. But the benefit here is really to have very good graphics, and that's why I would like to stick on this to understand some common wording. So what is a node card, what is a rack, and so on. Hence, you will see always these big boxes here. And this is, I think, very good examples, very big, bold racks with lots of blinking lights. It's always nicely also in the media when there's something around computing. But what does it really mean? And this is really different data access levels, storage access. We have seen already network topologies hidden, perhaps also in the second floor that we will see there, is below these racks. And, there's also different levels of caches. You have CPUs, basically multi-cores and many cores inside. And they are really different complex machines. They live in a hall usually, because then also you want, for instance, if there's a fire, that there's a gas protection and not a water coming on this fire. So take away the message that these is, of course, a very complex system design. Right, so combined, of course, with the whole infrastructure enabling huge power lines to have certain amounts of watts that actually also have to fuel these systems. These days, when we talk about exascale systems, I show you in a moment, larger systems, and also throughout the course, we talk about many, many watts. So you need the infrastructure for it. You need the whole with the, protection, and also then the cleanliness of the environment is also helping here a little bit, of course. And this is all important ingredients really to this HPC systems. And now when we then see this big monolithic blocks really, you will see that this can be, of course, put into much more smaller pieces. And we usually start with calling something the chip, This for processors could be multi-core here and so on. Then you would put them very condensed in compute cards, right? And then all of these different compute cards would then also, would be sticked very dense on a so-called node card. And these node cards, which is now really a big difference from what you know from laptops, right? Or from your desktop machines. These node cards are now very compressed. You see 32 compute as an example here for the BlueGene P. For the BlueGene Q, there was later then even more elements in it. And still the kind of terminology remains what I wanted to say you to this, right? Then they introduced something called a midplane, which were, let's say, something like a number of node cards. But still the message is like you have different node cards from the compute cards, and then they fill the racks. And then the racks is what you see here in this nice buildings all the time are then interconnected to the whole system architecture, interconnected as you have seen in the prologue video with all the cables and so on. These days we have even more infrastructure here and there. In other systems you will see here pipes, meaning there's warm water cooling these days. Elements we will also discuss later in the course, how essentially the infrastructure also affects the running of the systems. You can imagine we have to cool down these systems, and there must be different ways to do it. Some are basically air cooling, but also more and more we have liquid cooling, quite interesting technologies. But for you to take away the message is really these architectures change a lot, while the kind of terminology with chips, node cards, compute cards, racks rather stays, right? But there's of course mixed with different entities. Nowadays we have accelerator cards with it, and this is important. Equally, as I was said, the network topologies. So there are terminologies which you also should, let's say, if you want to dive deeper in HPC, also should know. There's, for instance, a torus network, mesh, and then also aspects we will cover later in the course about I/O. But here you see a little bit the compute nodes again that we have discussed, being connected then to so-called switches, also to the file servers. And you see here a little bit the bottleneck situation. Hence, we also should not think only about computing. Also, when you run a big, large, let's say, earthquake or lava simulation, you want to dump some point in time also the data, right, or the results. Hence, for all of these applications that I'm alluding here from different areas of physics and so on, this is also something to consider. They are not only computing. Hence, there's not only the interconnect important between the different nodes that you see here, and you see also that not only the neighboring here on the top, they're directly neighboring also then the next, enabling us interesting shifts, for instance, in the MPI communicator, I will allude to you later, with very high performance, moving through the systems if you want to have a wave propagation, for instance, and so on. So this is, of course, challenging in terms of task mappings on the exact communication. And in previous, let's say, iterations of the HPC course, we had a bit more on this. So we also have to sacrifice some of this because essentially we cannot put everything in the course, and we do more AI with HPC these days. But if you go later in some of the old recordings on YouTube, you will see much more on the network terminologies as well. So then coming to the developments, which is of course now, and you see the big AI here, and I think it's everywhere in the media, you know that, but we have really good results with AI. So it's a point why HPC these days is very close to AI, particularly in the areas of deep learning. Almost all of the successes we see in transformer models, large language models, all of that is basically enabled by HPC, right? So this is an important statement today. There's a key ingredient, which is general purpose computation on graphic processing units. So the GPUs I was alluding to indeed has its origin in computer graphics. Some of you know that for gaming, there were always GPU cards in a gaming computer. But now we talk about not using them for gaming, but rather for general purpose computation. And has certain benefits, not only being energy efficient, but also you see that the throughput character of how a GPU is tackling the problems is something what many scientific libraries also need. And deep learning is just a very good example of something we call matrix multiplication, matrix vector multiplication, so mathematical operations, which can be nicely parallelized. And with this, GPU is just beautiful. There are different programming models, and is not only OpenCL and NVIDIA CUDA, as I was alluding to. We have AMD Instinct cards as well with a different ROC toolkit. We have also approaches of standardization with HIP. And I will talk about this in the GPU lecture, a little bit how you program with them. And this is definitively one of the accelerators now that you have to put to the HPC system architectures today to make them as supercomputers as we have seen in the top 500 list. But we've seen also a really increasing number of more heterogeneity there, not only GPUs from, let's say, AMD and NVIDIA, we can see now also soon from Intel and others. Hence, let us just quickly go over some other sort of special units in this processing, which is FPGAs, which is basically a circuit that you really configure for a specific type. So this is a very specific way how you would program them. Hence, I would say these days it's not that far used, especially not in combination with GPUs. And also cell processors is something where has been, quite a promising line, but still the GPUs remain these days as one of the most dominant, let's say, new technologies, also because the GPU is not like a GPU. You have seen that when I talked about the top 500. So NVIDIA started from a long list from, maybe Kepler architectures, then coming over Pascal and Ampere, Volta, and so on, to this cutting edge chip they call now Grace Hopper cards, which are very, let's say, powerful. Some of them are particularly tuned for deep learning, so-called tensor cores. And we will make the case for it. But you know that also the technology is not just across all the different technologies, but also within this category of GPUs. Hence, it is more and more complicated to program these systems. Now let's say formalize a little bit what we now mean with such a many-core GPUs. Yeah, so that means for general purpose graphic processing units. Although you will see in the HPC community that we just talk about GPUs usually. So very rarely people talk about GPU still, right? It's all just GPU. But the origin and the original, let's say, idea is really this general purpose, which is a very important part. And here, in contrast now to what we learned with multi-core, we have now hundreds of these processors there. Now immediately you would say, well, didn't we said we overheat? And the trick to do this, to put them all on chips, is essentially to have them not as high single thread performance CPUs, but rather moderate performance. So they're actually having a less clock speed, but you put just lots of them on the chip. And with this you have, and of course lecture 5 will go much more into detail into this. With this you have a really high throughput that you can put through these processors. Although they're not the big number crunchers, CPUs, they essentially can tackle lots of different problems, and actually are today really one of the reasons why we have HPC in many different application areas. So this has solved something a little bit, coming with Moore's law, that we cannot have higher clock speeds and stuff, that had some important element in the past, but now with the GPUs we see really different impacts in this, that the kind of speed and system, let's say, scaling of potential capability is really enormous. However, the point of using a GPU is still a little bit limited by these two elements. We will also learn then more, of course, in lecture 5, that you always have to have usually the host CPU to fill the main memory in order to go to the so-called GPU device memory and then use a GPU. So this is a paradigm that has been a long time now used in GPUs, and is also kind of a bottleneck. But people work on this and have some solutions for this, but still it's not really, let's say, that a GPU as an accelerator, as we call it, stands on itself. So it always has to be part, or basically connected to a node, and we will make the case also in subsequent lectures. Hence, here we see several ideas how to use a GPU for different specific applications. So it's not that we use for everything a GPU, But if you have something, and this will be also part of lecture 5 much more, which you can nicely parallelize, right? Then it's just beautiful to do so. And here's a good example here of the color coding when you want to have, for instance, this matrix B, multiplied by vector C in order to get to vector A. You can follow this kind of color pattern with the orange here I provided to you. And then you see that essentially what you do in a deep learning network, which we will learn in a moment, is nothing else than lots of lots going through layer and layer, and then you have matrix, matrix, matrix vector multiplication. So you have just a lot of them. The beauty, however, in the color coding suggests I don't need the whole array, or the whole matrix for it, right? It's enough that, based on this mathematical rule, I have just this part of, the array B, this part of the on the matrix B, and this on the green just part of the matrix B. So hence I can crunch down maybe a huge matrix and a huge vector into smaller pieces without having any problems from the mathematics, because it's conveniently parallelizable, sometimes also called nicely parallelizable. And we will learn more about this in the lecture 5 and why this is so, let's say, impactful in HPC today is then really this deep learning that I also was already describing a little bit when we had, let's say, the prologue. So I don't want to go into this very detail anymore, just to have the pointer, of course, that when you have this deep learning networks, what I was suggesting is here's lots of matrix multiplications, matrix vector multiplication taking place. And these can be all quite nicely, for instance, in image recognition here, used to scale up on different GPUs, and with this obtain a significant speed up in really training those networks. That's not obvious to you. We see how that materializes when we come to lecture 6, and then also much more in lecture 7 when we use distributed deep learning. So we don't just use one GPU, we use maybe 1,000 GPUs in parallel to solve a problem. And then you quickly see that we can speed up significantly problems, which may be much more complex, actually, like this 10 digits here that we identify, right? This is, of course, not at all what a typical application problem is. This is just a toy problem in order to make you understand a little bit the key principles. And what we discussed now is really the difference here. We come to this in a moment, is not anymore what you see here, the different layers. What used to be the typical, let's say, artificial neural network time, let's say hidden layers that you see here. The idea is really not now putting more and more layers of the simple design after each other, but rather, as the video also will show in a moment, having a kind of smart idea really in these different layers in order to perform feature extraction. And this is what the convolutional neural network example shows here quite nicely. It extracts features and has feature maps essentially to detect features in images. So the layers you see are still feasible and existing, and also, of course, are basically from neurons and have connections and are trained over time. But it's not at all anymore so simple to have just the neurons or number of neurons there, but also different setups, convolution operations, and things we will learn in lecture 6 and 7. Now, the point for HPC here is really that this is computationally expensive, right? And these networks are now very huge, especially if you think like cutting-edge transformer models that fuel many large language models, and also in the end, then the language translation that we see is getting better and so on in many languages, because we have now computational capacity available in order to train these, deep learning algorithms, really. And with this comes a requirement for more and more technology innovation, hence fueling again, let's say, the different iterations of technologies from NVIDIA GPUs, as we have seen, right? So not standing still at the Kepler architecture or Pascal architecture from NVIDIA, but evolving over time, really with Volta, with Ampere, then now to the Grace Hopper, which is a fascinating chip we will see actually in lecture 5 already, and which is brand new from NVIDIA. So What can we do with it? So applications, I said, is the driver of HPC. So that's why we all do this. It's not just for fun and to be fast and to be the first in the top 500 or in the top 10. The idea is really having applications. You see here one that is around Earth observation. And this should also bring you to make you sensitive for another challenge in deep learning that you can't understand fully today, but it's also important to understand that HPC can help you there as well. So we have lots of data. The satellites that you see there nicely on the video are then also, taking lots of pictures, but these pictures are not just from the land cover. I was saying these are different spectral channels, up to 200 dimensions, really, and this become much more sort of a block. And with this, a sort of 3D convolutional neural network that you need in order to understand this. And this is just an example of a couple of publications I wanted to show you how you really need then this in real application. Because here we want to understand the land cover. Is it a forest? Is it a river? And we will do the window tensor, so basically a little bit around the surroundings of this pixel. So 9 by 9, for instance, which we described here, for instance, in this one paper of us, which is some time ago. But also you see the combination, for instance, of these technologies, which is another example here of this convolution operations with traditional classifiers called support vector machine. Hence, there are two things here. Firstly, you need lots of images and data to train them. Hence, your laptop might have not a problem, to do this in a small scale problem like MNIST, right? What we've seen with the character recognition. This is what you can do. But if you now come to satellite images and you have 14 million images, for instance, also in ImageNet, which is not a satellite imaging, but also, let's say, a cutting edge benchmark, then this would be the end of the laptop as well, not only from computing capacity, but alone from the storage you need to train these deep learning networks. And this is because there are so many parameters to learn, the weights that you have between the different layers. This is all not totally obvious to you. We'll come how that materializes in lecture 6 and 7 again when we have deep learning, because these weights are essentially then these matrix multiplications, the learning of them. Improving the weights is nothing else than doing lots of these operations where GPUs are very good. Now, the trouble and why HPC again is helpful is there are lots of these configuration parameters, we call them hyperparameters, in these deep learning models that you have to find and do the right, let's say, a justification for the different applications in order to have good performance. Hence, you see here a couple of them out of one of our papers. You want to understand the convolution layer filter size. You want to see a little bit which optimizer you use, stochastic gradient descent, or you want to have maybe some newer ones. You have different loss functions, what activation functions you choose, the rectified linear unit or others. The batch size is a very important configuration parameter for us, as well as the training epoch, so how long you actually train. And these are all elements which are not obvious, especially not the learning rate. So these are all names, which is, of course, for you, if you don't have taken a machine learning or deep learning course, a little bit of question mark. But take away the message that there's no very clear modus operandi how to choose them, right? There are some, let's say, best practices here and there. The rectified linear unit seems to be quite strong, but there's also others these days, which are often used. And you can basically, over many runs of the applications, get a feeling for batch sizes important, although they depend now significantly how high you scale into different nodes. So this is a complete, let's say, hard thing to do. And hence there are systematic ways how you can select and find these hyperparameters using HPC again, which is now saying that in one respect, GPUs have a big benefit in HPC to speed up the training, right? That's clear. We can do it quicker because we have just lots of GPUs where we can parallel program this training. And with this have a speed up, but it's not only the benefit. The other benefit we also communicate to our SMEs, industry partners, when we try to sell a bit why you should use HPC, is really the accuracy improvement by picking the hyperparameters right. And we have a new lecture even on this inside the course because it's getting so enormous momentum, where we'll then understand hyperparameter optimization much better than I can convey here at the beginning of the course, because we lack still some basics that we have to learn for this. Hence, this is also something what I already talked to you before. It's not only that, you know, you have then the idea of this computing, that it's only the training time in terms of speeding it up, the large deep learning networks, and you really need this, and also cope with big data, as we talked in the prologue about it. Now the point is also that this training time means training on different hyperparameters potentially. So you need, let's couple of times train the same model with different hyperparameters in order to get really to this high accuracy we see here. One small change in the learning rate, which we will see then in the hyperparameter section, can drop the accuracy significantly, right? Just because you choose a stupid, or you don't even know if it's stupid learning rate, it just doesn't work. And this is something which hyperparameter optimization then will go into. And that's why we use supercomputers like Juvels and all these different racks in order to speed up and then better the AI modeling as well, which has now grown, I mean, to a huge, let's say, I would say even more than a hype, right? So in AI, we have seen significant impacts. We have ChatGPT, which we will talk about with large language models later in the course. Many of you are probably using that on a daily basis. But this is not really a hype. It became more and more really a live impact for us, right? So it's really affecting our lives. Hence, there's also AI ethics. There's an AI office in Brussels coming now with also more and more regulations in the Union and in Brussels, how we can use AI and should ethically use AI and so on. So basically saying that, this is something where essentially this HPC is, required for these. Also from the cloud computing course that, there's different ways how you can really access these computers. Here you have an example of a cutting edge autoencoder from deep learning networks, and you can also do this in cloud computing because there's also the way of having more and more GPUs available. But in HPC, we just talk a bit different in terms of how you would, interconnect the cores. For instance, in HPC, the Apache Spark that we have across different worker nodes that some of you know from the cloud course that have been part of it. That is something what we see rather unlikely on a HPC systems, because we have other means to really communicate very quickly, like for instance using the MPI that we will learn in the next couple of course lectures. Just a little bit more to the data part before we close for today. The HPC relationship to big data is a bit indirect, but also probably a bit clear to you. So when we have a, let's say, earthquake simulation here, we talk about a terashake here, for instance, where the surface data is in the terabytes, or the petashake, where the surface data and volume data is in the petabytes. So of course, bigger simulations, right, where the inner scale is much more in the petascale fine-grained, which means much more calculations, and with this also much more data, where we talk about petabytes output really for this. That means automatically more computing, but also more data. Hence, your HPC system needs to also be ready for, this big data. And you could see that in HPC, we basically talked always about big data. Even 20 years ago, it was already large data sets that normal PCs could not really take care of. And the reason is that simulation sciences always, in a way, have a demand for more and more accuracy, right? More better earthquake prediction and so on. The trouble, however, is that technology is not really coming and follow suits perfectly. So we have seen that with GPUs brilliantly in the computing, but what we have still a little bit to tackle is the so-called DRAM gap that you see, that main memory is very fast, cache is very fast, and what happens then afterwards? So basically, the trouble is that our large capacities, we call that tape archives and so on, there's really where the petabytes can be easily stored. They are incredibly slow, right? And we will talk about this in other lectures too. But then, we have just disks, but they're also still too slow to really think about that. We have more and more computing, And the reason why we cannot just have lots and lots more main memory is also the cost. It is just very expensive compared to disks. Hence, there's a so-called, data challenge here, where we have a huge trouble in this data element, especially if you have these applications which are, as a symbol reaching out here, which are really big data compared to many other applications you might have. So this also drives the design of more data-intensive HPC architectures. Here's sometimes a bit older system, this gray wolf architecture, but you have dedicated server for dedicated problems, essentially, where you then do a bit like hierarchical storage management, and this by design. And this brings us to a whole world of data, just alluding to the point that essentially CPU speed is not our problem these days. We have rather I/O problems, right? So with existing HPC resources. So how we maintain the GPUs with lots of data in a high-scale production run, that should all come somehow, sometime from disk. And there's HBM, there's good, let's say, memory architectures now on GPUs available. But still, if you think about many applications and many users, and of course, not all systems can afford these, then you basically have troubles more on the data side, which I wanted to convey with this. Hence, the application co-design of HPC architectures we learned already in the prologue with this modular supercomputing example is taking this a little bit into account, as well as modern chips with NVIDIA, as I was saying, with the HBM memory, which is a very fast memory to fill the GPU with quite some data, because the capacity is getting bigger. But we'll also learn that there's still many gaps, and that's why it still says application co-design of HPC architectures. We still need more. And towards the end of the lecture, also just a hint, there will be soon Icelandic HPC workshops where would you invite you from the Competence Center here. Please have a look on the eHPC webpage to find out more. Here, I just wanted to make the case also that applications are still from utmost importance. It sounds so much technology, and it's important to master that technology. But you see with our simulation data labs, and they have that also in the Jülich Supercomputing Center. That's where we learned from this design of a successful design, really, of application support and application usage of these systems. We have different application domain specific labs. You will see them on the webpage with different experts in different labs that also have then the application domain experience, which is also very important in HPC to really scale up the problems that we have in all the different research projects, let it be large language models, or in RACE here, for instance, we had also lots of engineering and AI problems. Hence, we're working also in this, National Competence Center to have this, HPC community extended, building a community here in Iceland. And if you're going back, somewhere to industry, to jobs and so on, make the case that everybody's welcome to join our community here. Finally, I should just give a little bit of historical breakdown that, of course, now that we have the EuroHPC joint undertaking is a far development, which has been built on many, many years of praise. The Partnership for Advanced Computing in Europe, you have seen the video, which was the supercomputing infrastructure before essentially EuroHPC joint undertaking took over, where now the membership countries are basically directly involved in funding decisions together with the JU and the European Commission, often in a 50-50 case, where they decide also about the fundings, which supercomputers to put where, what technology, emerging technology to fund in terms of quantum and so on. The same is actually true for US at the XTEED. I had the good fortune to be part of this, the Extreme Science and Engineering Discovery Environment, HPC infrastructure in the US of the past. And then some aspects even go back to grid computing, a very old concept that was derived essentially from early ideas how you can do distributed computing and then combine this with middleware in order to solve bigger problems. You see here the Higgs boson was, for instance, one of the results that the found of this was just really working also not only from the accelerators and experiments at CERN, but also because they had combined this pooled computing they called grid computing in the past. Obviously, today with exascale, we are going to much other dimensions of scale, and hence it's getting, at least with the EuroHPC joint undertaking, let's say more and more professional, really, if you want, in the sense of provisioning of computing. You can apply for computing resources. There's a peer review. Others will judge if you should really get the system access. So it's a fair access system in a way to the demand. And with this, also the pointer that, of course, a cloud computing big data course talks a little bit more about this, although, praise has ended, exceed has ended. So now we have the UHPC JU here, and we will focus much more in this HPC course, particularly, of course, on some of the UHPC related aspects. So take away the message, HPC has come a long way, a long tradition. Where are we going in the future? Just as an overview lecture of HPC that we shouldn't miss, there's a nice, let's say, short lecture from me from 2020, which is still, I think, relatively up to date on YouTube, which gives you a little bit an indicator of something we called qubits and quantum computers. There's also quantum cryptography as a kind of course here. You have heard this probably. And, seeing basically that quantum computing could be and is considered as one of these accelerators, not like a GPU perhaps, a bit different, but optimization problems in machine learning, like here SVMs, for instance, or deep learning that we have learned in the previous lectures, is really something where also quantum computing can make a difference. And this is, of course, something which goes beyond the scope of this course, but it's definitely something where the EuroHPC joint undertaking, but also in general, the HPC community is very close to. The most that I wanted to convey today. Please have a look again on this PRAISE video. It captures the essence of many physical applications. And I would say that's all for today. So we'll talk about the practical lecture 1.1 next time. Talk to you then.